places, so everything is covered by fog. And
yeah, that is true. I mean, here also, if it is raining, it's not that. Maybe I can share the screen, right?
Yeah, you can keep the screen shared. Yeah, I can see it. So usually the classes are from 8 o'clock in the morning, right? In Trivandrum.
Yeah, so here it can start from 8:30. Some classes basically start from 8:30.
Okay.
Then, but it depends on the schedule. Like I think some of the students have till 7 or something. They might have breaks in between, but yeah.
Up to 7 p.m.
Yeah, I mean, it's not a continuous thing. They might have breaks, but yeah, there are some days where they have class till, because once they finish their foundation courses, they choose these electives, right? So this can be between even departments and so and so. So then their timings can be very odd because we have to, include all the students, their availability and professors' availability and so.
And the labs are probably longer, I think, after.
Yeah. So generally when they go to, once the major classes begin, I think half day is lab. And that too, it's not every day. It's 2 days or 3 days a week. We have like half days kind of.
Yeah, so good afternoon, everyone. Today in our weekly seminar, we have Dr. Shabnam Iyyani. She did her master's from IIT Roorkee and then completed her Ph.D. in Astrophysics under the Erasmus Mundus Joint Doctoral Fellowship from Stockholm University in Sweden in 2015. So after that, she did several postdocs. She joined as a visiting postdoc fellow at TIFR Mumbai, and then followed by Vaidya Raychaudhuri Prize Fellow at IUCAA Pune between 2016 to 2020. Then she continued her work at IUCAA as Inspired faculty until August 2020, before joining as an assistant professor at IISER-TVM. And as you will see that she is an expert in the study of prompt emission of GRV. So she will talk about more about that. And in fact, I know Shabnam from my PhD time. We did PhD under the same fellowship, this Erasmus Mundus Joint Doctorate. And I was posted in France and she was posted in Stockholm, Sweden. So we are batchmate. So welcome, Shabnam, and the floor is yours. You can start your presentation.
Yeah, thank you so much, Shvendu. So I should thank Shvendu and the organizers also for the kind invitation. I hope at some time I would be able to come in person and as well as visit IRIS and give a talk as well. And also thank you for the kind introduction. So today I'll be talking about a very particular topic, which it's one of the papers that we have published very recently. which is actually on follow-up to a previous paper that we had published 2 years back. And I thought it was a bit new in the sense both the work had something new to present. So I'll be focusing only on that in this talk. So as you can see, the title of my talk is basically describing the onset of particle acceleration and prompt emission of gamma ray burst. We basically know that all these high energy emissions that we see in the sky and whatever astrophysical phenomena requires particle acceleration in some form it to happen, and the process of how the particle acceleration happens, and also it's very rare actually to see an onset of particle acceleration to happen, because it's always the cooling of the electrons that we basically see as radiation, and that is what we always record. And but actually to see that something actually happens within the burst, and you get to see some of the dynamics related to it, is something very new. And especially in gamma ray burst kind of cases where it is just a transient and you get to observe one GRB only once, and it only exists for a very few seconds of duration. So to just begin with, I'll start off with the general introduction of what a gamma ray burst is, which might not be needed for most of the audience here. So gamma ray bursts are the brightest explosions that we know to occur in the universe. And what you see here basically on the background is the gamma ray sky as observed by the Fermi Gamma Ray Space Telescope. And when the gamma ray burst basically happens, it mostly outshines all the other very high energy gamma ray source in the sky. And this immediate gamma rays is what we basically record in all the space gamma ray telescopes, and is called as the prompt emission, which generally lasts only for a few seconds. And we know that they come from very far away distances in the cosmos, and they are believed to be narrow beam of intense flashes. And the second part to this event that we all know to exist is basically the afterglow, which starts after a certain delay, but it extends for a longer duration of time, and extending from a few hundreds of seconds to even days and months as well. And it is observed in all the multiple wavelengths that we can observe. And the classical picture that we have basically to understand the fireball, irrespective of what the progenitors are, whether they are merger of two binary compact objects, or if it is the core collapse of a very massive star, at the end, what we consider is that we have a very compact object, whether it can be a neutron star or a black hole, and it starts accreting the matter surrounding it, producing a huge fireball. So as the name suggests, what we basically have is a ball which is composed largely of radiations, and there is also baryonic matter present to it. Because of the high radiation pressure here, so it's the internal energy that basically gets converted into the kinetic energy, which then the outflow moves out and it comes out in the form of a jet. And as the outflow expands, at some point, the photons get decoupled from the plasma, and that's a point from where we expect to see some thermal emission. And because of the high variability that we have observed in the gamma ray light curves that you all might have seen, so because at the point once you are above the coasting phase in the jet, that is the dominant form of your energy is in the kinetic energy form. Now you have to think of some mechanism by which you can bring back that kinetic energy back into radiation. So that means you have to think of ways how to bring it back into the internal energy. So one of the mechanisms that is proposed is basically the mechanism of internal shocks. So that is where you envisage that the central engine, depending on the variability of its time, it is ejecting out matter as the matter comes out with a different mass and energies, and therefore they attain different terminal velocities. So you can envisage a scenario where a fast moving shell can go and crash into a slow moving shell, and this results in the dissipation of the differential kinetic energies of the shells, and the shocks thereby created is what we call as internal shocks, which basically happens within the jet. So this is generally where we expect the acceleration of particles happens due to the magnetic fields that has been generated in these shocks. And these highly energetic electrons basically then cool via various non-thermal processes, whether it can be by synchrotron or it can be by inverse Compton scattering also. So this basically composes of what we call as the prompt gamma ray emission, and that has been the main topic of my research. The jet may further go on and crash into the interstellar medium, and the shock thereby created is what we call as the external shocks. And the particles accelerated here basically gives out radiation in all the wavelengths, starting from radios to gamma rays, and this basically composes of what we see as the afterglow. Now, some of the key outstanding questions that has been in relation to, even while studying the prompt gamma ray emission, that is basically the emission that we observe in the gamma rays, is basically to understand what is the underlying radiation mechanism. So it's basically to understand what is the process that actually gives rise to the radiation that we are seeing. Is it the main competing models is basically, is the radiation dominantly coming from the photosphere that we are seeing, or is it coming from some non-thermal emission process like a synchrotron emission happening in an optically thin region that is a region much above the photosphere? And what are the dynamics of the outflow? Like, what happens to the Lorentz factor of the jet, or like where is the, where in the outflow is this radiation produced, and what are the dynamics of that happens in that point of the jet emission radius, and how it evolves with time, and so all are the dynamics that we always look out for while studying the prompt part. And also what is the composition of the jet? So this is also a competing thing to understand whether it is largely composed of baryonic flux, or if it is mostly composed of Poynting flux. That means we are asking a question whether it is magnetized or unmagnetized jet, and because this can play a key role in the dynamics of how even the jet, the classical picture I mentioned earlier is mostly for an unmagnetized jet. Now, if you consider magnetized jet, then the dynamics of how the jet evolves from the beginning itself would completely change. So, so this is also an important, is to probe the composition of the jet, and what kind of, if it is magnetized, then what kind of magnetic structures are present in that emitting region, and so on. And also we would like to understand is what is the central engine that is powering this jet, and what are its properties, and how it is related to the immediate environment surrounding it. So some of these questions is what we basically always try to understand and address in the study of prompt gamma ray emission. And it's mostly done by studying the spectrum. So as you all might know, the GRB spectrum generally looks very non-thermal in nature. So it's generally modeled using a phenomenological function called as the band function, which is nothing but two power laws that's smoothly joined at the peak, and is basically the low energy part of the spectrum is the spectral index is given by alpha, and the high energy part is given by beta, and the break is what corresponds to the E peak that we'll see in the spectrum. Now, how does this phenomenological model we connect to the physics of it is that because the synchrotron and the thermal emission that we saw that is expected from the black body basically have that is their simplistic models basically have very clear prediction of what kind of low energy part of the spectrum they are expecting. And so therefore what we gently do is that we gently compare the alpha values that we got to that of the theoretical values that has been expected, and we try to make an inference of what could be, whether it is non-thermal synchrotron, or it can be something that can be related to photosphere or not. So this is the general physics or the technique of how we generally kind of make inferences from spectrum. But this has a lot of limitations. So this basically has a problem, as what I just now mentioned in the previous slide is mostly where we look at phenomenological models. But as I said, just using any kind of phenomenological model is not enough at times to make an inference about the two models. For example, to demonstrate the fact, if you look on the right side for the example, I have shown the spectrum for GRB 0811 10A. So the orange plot basically shows the fit that you get for the spectral data that is mostly fitted using band. So one of the parameters, in addition to the spectral things that is also studied, is looking at the narrowness of the band function. So that is, we looked at the spectral width, which is nothing but the full width half maximum at the in the new plot of the best fit that you get to the spectral data. And you see that from the band fit model, we assessed that it was a very narrow spectrum, and that the conclusion was that as a narrow spectrum and it should be more related to the photosphere, and it was inconsistent with the synchrotron spectrum model that was expected, which tends to be very wide. So this was the inference that you would make, or one would make, just looking at the band function fit that is done to the data. But in green, what I'm showing is actually the synchrotron model fitted to the data. So the synchrotron model with the radiation coming from a Maxwellian distribution of electrons is what is fitted here, and we find that we can equally consistently fit the data with the synchrotron model as well. So this clearly shows that simply using the phenomenological model, sometimes because of the forward folding technique, the limitation of the forward folding technique that we have in the synchrotron and the spectral analysis, actually limits us from making a very clear understanding of what the spectrum is. So just by looking at the inferences made on the phenomenological model may not be enough for us to do that. So that means we need to directly test the physical models with the data. That is one way to go forward. But then again, the problem is, if you look on the left side, that is where I'm showing a spectrum for GRB 110928, I have two competing models, which I said is one is the photospheric and one is basically the synchrotron models. So here in pink, what is shown is a Comptonization model that you have presented with a power law, which is shown in pink, and then there is a black body plus synchrotron, which is a classical fireball picture that we have. And we can see that both the models are actually equally consistent with the data. Their physical interpretations are very, very different. Okay, so in one model, in the Comptonization model, we are basically actually looking at a subphotospheric dissipation model, where the dissipation energy of the kinetic energy of the jet is basically happening below the photosphere. And that is giving rise to the Comptonized spectrum that we are seeing. Whereas in the other model, that is the blackbody plus synchrotron, the physical picture is such that you have a black body which is just coming from the photosphere, and you have the classical picture where the dissipation of the kinetic energy is basically happening above the photosphere in the optically thin region. And we can see that both are equally consistent with the data. So this degeneracy that exists between various models, how to break them, and to help us understand or help us constrain what could be the the correct spectral model, is the main limitation that we currently face while doing spectral analysis. So in this aspect, what I want to present is the spectropolarimetric observations of GRB 160821A. So in addition to what the information that we have, that is in spectrum, we have the distribution of how the photon energies are distributed with respect to energies, just the spectral information. In addition to that, if you get the information of polarization or how the radiation is oriented, if it has any kind of preference to its electric field orientations, will also give us some insight, can also help us constrain what could be the radiation process. And this is again because the different models basically have a different prediction of how their polarization properties would look like. And using this, this study was made possible because AstroSat, the cadmium zinc telluride imager instrument onboard AstroSat, is capable of making polarization measurements, and it is also observing GRPs. So with this, capability, we combined the spectral information. So this GRB 16021A was observed by both Fermi Gamma Ray Space Telescope, and it was also observed by AstroSat. So we basically used the spectrum because Fermi provided an extensive spectral coverage starting from a few MeV, kV till there was lat emission, so it extended till a few GV. So there was a very elaborate observation of spectrum that was provided by Fermi, whereas AstroSat observed mainly the information that we particularly used for our study was the polarization information that was collected basically within 100 to 300 kV energy range. And so to describe you how that event basically looked like, so the prompt emission part of the GRB in the light curve, basically it triggered, and there was only a very soft, mild emission which extended for nearly 112 seconds or more, so more than 100 seconds. It was only dominant in the energy range 8 to 10 kV MeV at a maximum. It was mostly like there was no much detection in the BGO detectors at all. So it was mostly modeled using exponential cutoff, because there was not much higher emission at all that was present. And it had a very typical non-thermal behavior, with the alphas being very soft, and it was roughly around -1 and so. But the interesting thing was, after 100 seconds, we had a second emission episode, which was actually nearly 100 times more brighter than the initial episode, which extended for a duration of, very long duration of 100 seconds. So, and here the emission actually extended from 8 kV to 200 MeV, but there was also extended emission that was observed in LAT, which went till roughly around 4.5 GV emission was also observed in this. And there was a very prominent LLE emission that was between 30 to 100 MeV. There was a very prominent emission that was observed during this episode of the burst, and this is what we generally refer to as the main episode of the GRB. And it was only this episode which was actually recorded in the AstroSat detector. And the first emission part episode of this GRB was not clearly seen in AstroSat, but this main emission episode, which was extremely bright, was observed in the AstroSat. And actually, with the flux brightness, it makes one of the most among the 10 brightest GRBs ever observed by Fermi Gamma Ray Space Telescope. So it has been very bright indeed. And the spectrum of this main episode was actually quite different from what we otherwise generally see, because we generally fit it with a simple band function. But here what we saw was that the Newton plot of the spectrum actually had a very broad top hat like a structure, where so the band function had to be multiplied with a high energy cutoff power law. So there was an extended power law. So the high energy part of the band was more or less flat, and you had to have an extended power law, and then very high energy cutoff was required. And the spectral shape looked like something as I've shown here on the right top. So so there were basically we had to use a black body. So in the first paper that when we did, we tried to model. The spectrum was very complicated. Actually, it was very difficult to get it modeled in the beginning, because it did not fit into the traditional norms of the kind of spectra that we were generally fitting to GRBs. So we had to use a black body, and we used a band and a high cut. So, but the main takeaway point I would say from the spectral fit analysis was that the significance of the need of the black body, even though it formed only a very small fraction of this entire spectrum, was very, very high. So basically what it meant is that, instead of in a traditional band function, you would just have one break, right? That is the E peak. But here we actually had three main breaks. So there was a peak or a break that was provided by the band, the black body the peak, and then there was a band break that was coming from the e-peak of the band function, and then there was a third break that was coming due to the high energy cutoff. So that was the main aspect of it, which provided this kind of a shape. And if you look at the how the spectral parameters evolved during this burst emission, we see that most of that is the alpha that is shown in the upper panel of the plot. What I plotted is alpha in black squares, and in blue circles is basically the high energy power law index, that is beta of the band function. And you can see that throughout most part of the burst, the alpha is very steady at around -1, whereas the beta function is showing some kind of getting, like, it gets softened, and then after some time it tends to show, tends to become more flatter. And the lower panel is all the peaks of the spectrum that was given, basically one that you can track by looking at the temperature of the black body that is shown in the green triangles. And then you also have the band e-peak, which is shown in black squares, and in the cutoff, which is shown in blue circles. And you can see that again, the two low energy peaks, which is provided by the black body and the band e-peak, are very steady throughout the burst, whereas the only thing that shows some trend of evolution is basically the high energy cutoff. So this was the main thing that we could understand from the spectrum. Now, the interesting thing came when we actually did the polarization study of this burst. So when we looked at the entire burst interval, that is the main emission episode of this burst, what we found was that it had a very low modulation in the Compton scattering curve, which is shown in the upper panel on the right side. And you see that it had a very low polarization fraction value, and it was constrained at 90% confidence level. And when we look at the contour of basically the polarization fraction versus the sky polarization angle, we find that there was a hint that there was two preferred polarization angles which is present within the entire burst sample. So there was a hint of why it seemed to be very unpolarized and the time integrated emission. And this was further confirmed when we were able to do the temporal analysis of the polarimetry data. So generally, the temporal analysis of GRBs for polarization is very difficult, generally because we don't have enough number of the Compton events recorded in the instrument, and the scarcity of photons is always the issue. And when we have to divide it into several bins, it becomes more difficult. And but fortunately for 160821, we had enough number of photons, and what we did was that we broadly classified it into 3 main intervals across the burst. And what we particularly saw was that between these 3 intervals, the polarization fraction seems to be very high, and as what is shown in the upper panel of the bottom curve. And whereas the interesting thing was about the polarization angle. The polarization angle actually showed a flip or a swing by 90 degrees between the rise and the peak, and the peak and the decay part of the curve. So so this, there is a, because when we did the time integrated itself, we got a hint that there can be possibly 2 angles that are present in it. But here it was interesting that the angle got flipped by close to 90 degrees between these 2 rise and the decay phase of the burst. And this basically also confirmed our understanding why, when we take a time integrated polarization measurement of the burst, it looked generally unpolarized. But it was very curious because why would the polarization angle swing by this certain angle between this burst? And connecting to that of spectrum, if you remember that most part of the spectrum, especially the low energy part of the spectrum, was very, very stable throughout this. The only connection that we could see was that the high energy part of the spectrum, that is that basically the beta and the high energy cutoff, was the only component of the spectrum that actually evolved with time. And we saw that this rise and fall in the cutoff we basically see is actually consistent with this change flip in the polarization angle. So there is some connection to the spectrum, but the thing is that it has something to do with the high energy part of the spectrum. Now, because this burst was very bright, and therefore it was fair enough for us to assume that the GRB jet was oriented towards us, and that whatever we are viewing is within the jet cone. And with this understanding, if you look at the polarization fraction that we can expect from the different radiation models, so what I plotted here is basically on the y-axis is the polarization fraction that you would expect within 100 to 350 kV of observations, versus on the x-axis is the ratio of the viewing angle versus the jet opening angle. And we see that anything within 1 means we are viewing it within the jet cone, and anything outside the 1 means your line of sight is lying outside the jet cone. And we have plotted the curves basically for the synchrotron emission that is coming from an ordered magnetic field, that is what is represented by STO, and is for synchrotron emission, and that is expected in a random magnetic field, which is shown in the solid black curve, and that is expected from an inverse Compton scattering is shown in green. And you can see that the high polarization fraction, because we are viewing it within the jet cone, we have to look in the region which is where Q is less than 1, and we see that high polarization fraction is clearly predicted only by the synchrotron emission that is coming from an ordered, highly ordered magnetic fields. So the other two models are basically ruled out. But what we say is that, so at least this combining the spectrum as well as that of the polarization measurements, we can say that what we're seeing is a synchrotron emission, the radiation that is coming, and it is basically at least the magnetic field structures, what we can strongly comment on is that at least within the 1/gamma cone that we are observing, it is ordered. It has an ordered structure to it, largely an ordered structure. Now, interesting was that, as I said, the main emission episode of this burst basically started nearly 112 seconds later. And that even extended for nearly a duration of 90 seconds. And we had a very clear detection of an afterglow also, because there was a measurement basically in optical. So there was an extra power law component which actually clearly started to show as an extra power law component, that it did not fit into the other extension of the high energy part of the spectrum that we observed earlier in the major part of the GRB emission. We actually needed an extra power law. It was statistically very significant, and this power law component emerged in LAT at 153 seconds, and later it extended for even for a very long duration, more than 2000 seconds or so. And optical emission was actually observed by an optical observatories on ground nearly half an hour later, and it peaked at around 2000 seconds, and which is so the afterglow, whatever information or data was available, that is what is basically shown in the plot here. The blue squares basically represents the optical curves, the flux data evolution with time, and you can see it kind of roughly peaked around, we cannot clearly say it's a peak, it's just one single data point that we have, and it showed a decaying curve, and it was only upper limits at later stages, and radio observations were actually carried out for a later period of time for a number of days, but there was no significant radio emissions that were observed. And there is a tendency for a break that can be someday between day 1 and day 4, because just looking at the trend of it, of the optical light curve that we are seeing. But since we do not have much information in other wavelengths, we cannot completely confirm whether it is an achromatic break that we are seeing related to the jet or so. Yeah. So from this paper that we had published in 2019, what we basically confirmed was that synchrotron is the main radiation process that is giving rise to this emission that we are seeing. So this was made possible because of the combination of spectrum and polarimetry that we had. Now, if synchrotron is the model, then definitely the way forward would be that we should directly go and test the synchrotron model with the data instead of using because we had used a phenomenological function. So we wanted to test directly. If we're seeing it as synchrotron, then we should go ahead and do that. So that was what we did in this paper, which is published this year. And what we clearly saw was that, so let me explain the kind of electron distribution and the synchrotron emission model that we used. So because we have some information of the afterglow that we have seen, and also we have seen the burst prompt emission, which is very, very bright. So we kind of looked at what could be the radiation efficiencies, and we found it was quite high. And since it was very bright, it was more reasonable to consider a fast cooling synchrotron emission model. So that was what we basically considered. And we basically looked at a broken power law distribution. Okay, so since it was a fast cooled synchrotron emissions, on the left panel, what I'm showing is the electron spectrum distributions that were obtained for the 3 intervals. So in this work, what we basically did was that we only looked at the 3 intervals where we had clear polarization measurements. So we did not do an extensive temporal analysis, but instead what we basically did was that we just looked at the behavior of the synchrotron model in these 3 intervals within the rise, peak, and the decay phase of the burst. So that is basically denoted by here the interval 1, which is during the rise. Interval 2 is that is a peak, which is in orange, and interval 3 is basically the decay part of the curve. And we basically used a broken power law with an exponential cutoff at the higher end. This was required because you also saw the spectrum, that the spectrum was not simply extending as a power law. There was a clear cutoff that was observed at the higher energies. So this was required in the electron distribution spectrum as well. So we basically only used a broken power law with an exponential cutoff. Now, since we are assuming it is fast cooling, the low energy part of the spectrum was kept fixed to, the index was fixed to 2. So which basically in the nu of nu gives you a flat spectrum. That is what you see, the low energy part. And then you have an break. In the electron distribution, there is a break, after which there is a power law and there is a high energy cutoff. So the power law index is basically given as the P value. And what the synchrotron model, so when we tried fitting these 3 intervals, what we interestingly found was that the interval 1 and interval 3 was consistent without a power law. That means we just had that flat power law, the low energy part of the spectrum, and it kind of decayed abruptly after that. So there was no need of an extra power law in between. It was not at all required. And if we basically try to fit it with that, the results were very bad, and it was statistically also clearly not required at all. Whereas when we come to the interval 2, that is a peak part of the spectrum, what we find is that there was a clear presence of a power law which was required, and a high energy cutoff that you can clearly see. So this was the major outcome of this work, because what we actually is seeing here is that there is an onset, because initially there is no power law that we are seeing, whereas in the when it comes to the peak, we are actually seeing an emission coming from an accelerated power law of electrons. So what we are actually seeing, so you're actually seeing a power law distribution there. So this basically is showing you the onset of particle acceleration that is happening within the burst. So you might remember, we have seen the main episode. So it's just the 3 parts of that same light curve that we are seeing. Where we are seeing is that the higher and low energy part doesn't show that, whereas the middle part is actually showing you a presence of a power law acceleration that has happened in the burst. And we constrained the power law index, which is basically p+1, because it is because the electron distribution that you're finding is basically the cooled electron distribution that you're looking at. So it will be basically p+1. And we find that it kind of is found around 2.3, so which basically tells that the accelerated power law index is roughly would be around 2.3, which is what is expected in line with the studies of particle in cell simulation studies that are basically done by Fermi accelerations. What we expect is something to lie between 2 and 2.5, and that is exactly the value that we are finding. So, so this is in line with the expectation of particle acceleration, which is expected to happen in a weakly magnetized outflows. And that's what we're seeing. So once we kind of knew the synchrotron spectrum and we saw it, what basically we can always do is that we can calculate certain number of parameters associated with it. So one is the number of radiating electrons that we can calculate. So that is basically if you take what is the flux that you would see, or the luminosity you see at the cooling frequency, and you can basically divide it by the power that you would expect from a single electron, and you get an estimate of how much would be the number of the radiating electrons that you would see. And the second important part, so for acceleration to happen, because we see acceleration to happen, we wanted to investigate the properties that would actually help to decide whether acceleration happens or not. So that means because there is something that is happening, because of which we see that earlier there is no acceleration, and then suddenly there is acceleration of particles, and you see some emission, and again the acceleration goes up. So that means there is something that is happening in the dynamics in the emission side, which is basically telling you, there is something is getting qualified for acceleration to happen, and it's not. So in the particle in cell simulation studies have clearly shown that one parameter that would help you to decide this is basically the magnetization that you can calculate in the downstream of the shock. That is the shock part of the jet when you're looking at the magnetization that you can see in that part of the jet. So this is something that we can calculate, and we basically estimated those. And so within the burst, so here we show the temporal evolution of how these three parameters, basically the number of radiating electrons, the magnetic field intensity is a parameter, it's a pre-parameter in the synchrotron spectral fit itself. So you get it directly from the spectral fit, and the magnetization of the parameter. So generally when we do the fit, the magnetization, the magnetic field intensity is basically in the observer frame. So in order to look at the co-moving magnetic field intensity, we need to assume some Lorentz factors, and which is also required in the other parameters also. So for certain fiducial values of gamma is equal to 300 and a redshift of 0.4, we basically estimated these values, and this is what is shown here. And we can see how it evolves. So the most important thing is that if you look, the number of radiating electrons, it is basically increasing from the first to the second interval. Okay, so I'll focus here more on the first and the second interval because in terms of polarization also, these were the two intervals where they were statistically very significant. And here also you can see all the properties very clearly how it changes. Actually, the number of counts actually decreases significantly when you go to the third interval. So just for more clarity, we'll focus on these two intervals, but we have seen the behaviors consistent with others, as you can see in the plot. So we see that the number of radiating electrons are basically increasing from the first interval to the second interval, whereas the magnetic field intensity, the co-moving magnetic field intensity does not change much. Whereas when you look at the magnetization parameter, there is again a significant change. That is, it basically decreases by several factors between the first and the second. So this was the striking features that we can see. So the certain dynamics within in the emission site, we are basically seeing certain properties to clearly change between these two episodes of emission. So we basically consider transverse shocks. So that is, we are considering the magnetic fields which would dominantly remain in the shock field would be that which will be perpendicular to the normal to the shock front. And so in those cases, it has been shown in various particle in cell simulation studies that the magnetization that you can expect in the upstream would be several fraction of what you would see in the shocked region. So that means the shock is basically moving into a lesser magnetized region. And this is consistent. This is a picture that we would expect if it was moving into a weakly magnetized. The shock was moving into a weakly magnetized region. Now, for the particle acceleration to occur in such kind of a scenario, the condition is that the downstream magnetization that we basically considered has to be less than a certain critical value. Okay, so so if you basically, so what it brings about is the relationship that I've just shown here is that the relative Lorentz factor across the shock front would be related to the downstream magnetization, which is a function of the bulk Lorentz factor of the jet by the relation as it is shown here. So it has to be less than a certain factor of this. So this basically gives us a relation showing that the relative Lorentz factor of the shock has to be inversely proportional to the bulk Lorentz factor. So this plot is something that you can generate easily using the relation that I've just shown in the previous slide. Now, the black line, the power law that is shown here is basically the condition where the relative Lorentz factor of the shock front becomes equal to that of the bulk Lorentz factor condition. So now if you take that, now in the peak bin, so there's a condition. So the condition for the particle acceleration to happen is that the magnetization in the shock region of the jet has to be lower than a certain critical value, which is given by the gamma r. Okay, so that means in the orange curve, which is denotes the peak interval, where we actually clearly see acceleration has happened. So that means there is particle acceleration happening. So that means that the condition that the magnetization in the downstream has to be lower than the critical value is satisfied. So if that has to be satisfied, then means the bulk Lorentz factor has to be lower than that vertical line, orange dashed line that we have shown. Okay. And whereas in the other two intervals, that is interval 1 and interval 3, which is given by the blue and green respectively, you can see that there we don't see particle acceleration to be present. So that means we can definitely reason that their magnetizations are actually lying above that critical value, and that is why we don't see any particle acceleration there. So if that is the case, then means the Lorentz factors, bulk Lorentz factor is actually larger than these values that is marked by the green and the blue vertical lines you can see. So in this basically, so this gives you a lower and upper limit. So combining these two informations, we can say that the bulk Lorentz factor of the jet is basically lying something between the between 400 and 800. So somewhere it's lying between these two values. So this estimate of the bulk Lorentz factor we have now made by using the condition of onset of acceleration, whether we see it or not. And similarly, so once you know the Lorentz factors and you know the time when the burst emission and the main episode of the burst has happened, you can definitely calculate what is the emission radius, and we find that it is of the order of 10 to the power 18 to 18 centimeters. So this is quite large than what we generally expect. In generally we say afterglow is expected at radiuses of 10 to the power 16 to 10 to the power 17 centimeters, but here we know that the afterglow emission we are seeing is much later at times of 153 seconds or later. Half an hour later is where we actually are seeing the afterglow emissions. But here a main episode of this emission has happened because now we have got a clear estimate of what could be the range of the possible values of bulk Lorentz factor. I have given the corresponding range, so we can clearly see that it is of the order of 10 to the power 18 centimeters. So with this information, we kind of give you the physical scenario of what could have happened. So we know that the long GRBs are basically expected to be produced by the death of very massive stars, the core collapse of very massive stars, and a kind of these massive stars, what we expect are to be the Wolf-Rayet stars. And we know they are extremely massive with luminosities much larger than their Eddington luminosities, and during their existence, they kind of eject out a lot of their matter surrounding. And in a small fraction of these Wolf-Rayet stars, there has been a ring of nebula that has been actually detected in some of a small fraction of Wolf-Rayet stars we have seen, and majority of them are found at a distance of roughly around 1 parsec from that stars, which corresponds roughly to a distance of 10 to the power 18 centimeters, which is consistent with the emission radius that we are seeing. So what we are proposing is that in this burst, what is basically happening is that the initial episode that we might have seen is maybe due to some kind of internal shocks, is the general, the emission of jet that we have actually seen. And but the main episode that we actually observe is to be as a very strong flare of emission that has happened is basically coming because of the interaction of the jet with this ring nebula that has basically happened. Basically, so this, as you can think of, it creates the shocked region where we can have the forward shock, where the electrons basically get accelerated, and you see this, all the dynamics are mostly happening in the forward shock. And as you can see, so one proposed way of explaining the two having no acceleration and then an acceleration. One possibility is that because there can be a large distribution or difference in the particle density that is present in this nebula. So when it has actually interacted with when the jet interacts with a region of the nebula where the particle densities are very much larger, is the way where the magnetization can drop. So magnetization is inversely proportional to the number of particles. So as you can clearly see that when the number of particles increases, that is when the magnetization actually drops. So it can be possible that in the forward shock itself, so when the jet interacts in certain part of the nebula where the particle density is much higher, is where you actually see an onset of particle acceleration and gives out high radiation, and that is basically what corresponds to the blue part of the curve that we are seeing. And the remaining parts, wherever it is not, is what may be the underlying, there might be some emission that may be underlying already produced because jet's interaction with other part of the region of the jet where it is not where you don't, or the jet has not experienced very large increase in the particle densities. So this is one possible case. And the other thing is that, for most important thing, this again is a picture that we are presenting, but this clear understanding of what causes the change in the polarization angle that we see is not fully understood. But what we propose is that, because we now clearly see that there is acceleration that is basically happening. And we from the polarimetry, we consider that there has to be an ordered magnetic field that is present, right? But if the acceleration of particles has to happen, what is required is a randomized magnetic field that is required, that might be produced in the shock itself. And when we see that there is a dominant emission of particle acceleration and the emission that is happening, it is mostly possible that the dominant magnetic configuration at that point might have slightly changed, and it might be dominated by the randomized magnetic field. And the other ways, in other cases, it might be dominantly by the toroidal magnetic field or whatever that has been already present on a large scale within the jet itself. So that can be one possibility that we can think of, and that might be the reason that the angle changes by so actual value of the change in angle is roughly around 80 degrees, but plus or minus 10. So that is why we always say that it can kind of swung by an angle of 90 degrees or so. Yeah, so it basically, there is a change in angle, and that is consistent with this very bright emission that we are seeing. And what we are finding is that during that bright emission, there is a clear signature of particle acceleration that has happened. So this is a kind of proposed scenario that we are putting forward in the paper. So the main takeaway from this entire work that we have done in 2 papers is basically that spectropolarimetry actually allowed us to confirm that the radiation is coming from synchrotron. So the results or the follow-up analysis that we have done makes more sense, or more becomes more convincing, is because we were able to pinpoint the radiation process. Because in otherwise the scenario is like there is always degeneracy, that even subphotospheric dissipation models can also produce kind of very broad shapes that we can have. Then it's a question of, we don't know whether it is synchrotron or whether it is subphotospheric or so. But here the polarimetry played that key role, where it gave us that extra bit of information, which actually kind of disentangled the degeneracy and told you that, okay, the radiation has to be synchrotron, and there has to be some kind of large scale ordered magnetic field present in the jet. And the follow-up study that we did, based on, because we now know that it is synchrotron, and the synchrotron follow-up modeling gave us the clear picture that there was an onset of particle acceleration into power law, which was happening during the peak phase of the burst. And the most important thing we notice is that the number of radiating electrons is basically increasing during that period of time, which is you see that is the reason why also magnetization kind of drops, which allows for the particle acceleration to happen. But we don't find the magnetic field intensity to change very much at the same time. And the gamma and the cooling frequencies and the minimum Lorentz factors of the polarization fields, the power law spectrum of the electron distributions are not very far apart. Actually, they are very, very close by. So even though it is we consider it as fast cooling, so that it lies above the cooling frequency, but it is most likely that what we're looking at, it's like a marginally fast cooling synchrotron spectrum that we are looking at. And what was interesting was that with the study, seeing a transition that is happening from acceleration to non-acceleration is actually giving us a new independent way of how we can constrain the bulk Lorentz factor of the jet, as I have showed you in the previous slides. And the most important thing is that if this scenario, what we mentioned, this flaring that we are seeing, late time flaring that we are seeing, and if this kind of property is to be observed, if, as we suggested, this has to be caused due to the interaction of the jet with the nebula that is present, then this kind of light curves or emissions would be observed only in a fraction of GRBs, because, as I mentioned earlier, it's only for a 10% of cases that we have seen Wolf-Rayet stars to have this kind of nebula structures around it. So yeah, with this, I come to the end of my talk, and I would be happy to take questions.
So thanks, Shabnam, for this wonderful talk about the prompt emissions in GRVs. And we have time for question and answer. So please, you can unmute yourself and ask the question directly, or put the question in the chat box.
Hi, Swendu. Can you hear me?
Yes, go ahead.
Hi, Shabnam. Thanks for the nice talk. So I have a question about the radiative processes. For example, in this source, you find the radius of the emission region is very, very large, like 10 to the power 18 centimeter.
Yeah.
And generally in the end, then what you found is like the jet is particle dominated, and as well as you have the burst emission where you have many target photons. So is there any implication for, for example, inverse Compton radiation?
Yeah, so inverse Compton was also something that we kind of probed to explain that kind of spectral feature, right? You are saying that the spectrum can be very broad. Is this what you're trying to say, that it can also be produced due to inverse Compton scattering? If I'm getting your question right.
Yeah, I can hear you.
Yeah. So we did try explore that factors as well, irrespective of what we get the information from polarimetry. But we find that is not likely possible. Is the reason is because we see clearly a break at the high end, because see the cutoff here, what we see is actually quite high, and we can clearly see that. And if it is in that very bright part where we are seeing high energy cutoff, we would also expect to see, multiple other, because it's optically thin
for
region,
example,
right?
like you have the large radius, so attenuation effects will not be very important. If suppose there are any like TeV photons produced or something like that.
No, so at least for this burst, there has been no such observation made yet. And as I said, we don't see any signatures of other multiple peaks in the higher energies, or even at at lower normalizations also. So yeah.
Okay.
The only thing
so
that
I have
we see,
one more question. Like, so is this very unique GRB where you find the large radius, or you have some other objects as well?
Yeah, so this is an ongoing work within the group that we are actually extending and searching for such similar cases. So what we actually found was that it does not seem to be a unique case.
Okay.
It seems to be there are cases which has this similar kind of properties.
Okay, thank you.
Yeah.
Hi, Shabnam. It's Ankur here. Thanks for a very nice talk. So my question is about that Wolf-Rayet nebula you have mentioned in the last slide. So if you have this Wolf-Rayet nebula kind of structure, so what kind of GRB light curve we should search for this Wolf-Rayet signature or the Wolf-Rayet nebula signature?
Yeah. So what we kind of understand from whatever the physics that we have did here, the physical picture is that if it is this, so because most of these nebula structures are generally, it's like a hollow cavity where only a ring of the material is present at a very large distance. So that means the jet would be able to move through without much difficulties, but only at a later stage it would actually interact with this dense matter, whatever is present. So what we expect in such scenarios is that there should be kind of a late time flaring that you should see in the prompt emission part of the GRBs. So starting from its trigger, we would be expecting that we should see some late time flaring. So yeah, so that is the main, if you look in the part where I said, so if this is the kind of scenario we are looking, we only expect that only a small fraction of GRB should have this kind of very bright late synchrotron pulses. So the signatures that we would look out for is something like this, that we would look out for very bright delayed bright prompt emissions starting from the trigger.
Okay, and so I have another question regarding this. So if you have this Wolf-Rayet nebular kind of structure, so there is some optical thickness is also very high at this region. So should we expect some thermal signature at this region along with the non-thermal one?
So this is something, it might be possible, or because we do not have too much of information of what kind of densities and optical depths we have to expect in these kind of nebulae yet. But this is something we'll have to do and look out for, because if such kind of interactions exist, then this is the one way that we can actually probe the structures as you have mentioned. So looking at the densities and so and the scale of the object and things. So yeah, but largely I would at these very large radiuses, we would not be expecting too much of optical depth. That would be my expectation. But yeah, this is something that we'll have to explore and see if we do see some emissions. And then the question would be, we will have to kind of decouple the differences, whether they are basically associated with here or if it has any other association with the other jet by itself or not, or so. Yeah, but this would be something that needs to be probed.
Okay, thank you.
Yeah, so I also thank Ankur for asking the question, because I was going to tell the students that they are not asking, they're completely silent and not asking any questions. So Ankur saved them actually. So anyway, so are there any further questions or comments or suggestions, anything? Shabnam, so I have just minor things to ask. So in the spectropolarimetry, these observations are from which instrument you said?
CGTA onboard AstroSat. Yeah.
Okay. Okay. So this X-ray polarimeter that is going to be launched, that will be helpful for this kind of study.
Yeah. So if it observes in 100 to 300 kV, I at least like higher, because if you say even in the spectrum, if you are looking at basically 100 to 300 kV is actually a very small region. So it's mostly, but still we are looking at roughly around the peak of the spectrum, because GRB spectra roughly peak around a few hundred kVs. So interesting thing actually, if I would personally would say, is that for GRBs, even if it is distinguishing between two photospheric and the synchrotron emission models, it would be best to look at a little lower actually, the lower part of it, because even in photospheric models, the peak is generally expected to be not okay. I mean, I would say it is both ways. It's like if peak is there, generally what people expect is that if it is photospheric, even if it's subphotospheric dissipations, the peak would be roughly unpolarized for photospheric models, whereas for synchrotron it would still remain polarized largely. I mean, if it is ordered magnetic fields. So that is a kind of distinction that people try to look out. But if it is a little lower, then you would see some signatures of polarization for other models as well. So yeah, so it depends on, and also the sensitivity, and I think the temporal dynamics of polarization is very interesting actually. So till now, whatever instruments have flown internationally also, what they've been capable of doing is that in GRBs, we have been only able to make time integrated polarizations for majority of the cases. Yeah, but we find that if we are able to do temporal studies, it can be much more informative and can really be helpful in deciphering various radiation models.
Okay, so if there are no further questions or comments, let's thank Shabnam again for this talk, and I hope that you could visit us sometime here at Aries.
Yeah, sure.
We could have
I look forward to that.
Yeah. So with this, we'll close for today, and we'll meet again next week. Bye bye.
Bye. Thanks.